Here we go. Oops, here we go. Functions as power series. This one is probably the most commonly used one. Here is the power series for the inverse tan. Here is one for the natural log. I'm going to show you some more. Well, actually, I'll start off with a baby one just to get us into the swing, and then we'll look at some more complicated ones. So, suppose I would like to get the power series for that. And I'll write beside it, if you like, the building block, the guy that we're going to use. Now, this fella here is going to go there, right? So what that tells me is that my substitution, my replacement, if you prefer that word, for x is this case is going to be 2x, right? Oops. Use the original. So it's going to be sigma n equals 0 and to infinity 2x to the n. But I have some terms on the top. You know, sometimes it's x squared. In this case, it's 10x. And I can stick them on the outside for the time being. And then we use a piece of algebra that says you're allowed to bring these things inside. And there's another bit, style points, that says this is not a good way to write it. So I'm going to split this up as 2 to the n, x to the n. And then I'm going to bring in a 10x. And then I'm going to put the whole package together. And that x will join this x and now have an n plus 1. That 2 to the n is going to stay put, and that 10 is going to stay put. Now, it's not that that's wrong, but couldn't it easily be confused with 102 to the power of n? So it's not uncommon that you put a bracket around that guy, or I'm just showing you some of the different ways that you may choose to write it. You put a bracket around that guy, but you find some way of separating the two guys so that it's clear that it's a 10 times a 2 to the n, right? So you can make that the fella, you can make this the fella, whatever you want. There is a third way, which I suggest that you don't do, especially in WebAssign, is that you emphasize the multiplication. And because if you do that, can't it look like 10.2? And that's not really what you want either. So I would refrain from that version, although you may look online and see people doing it. Right, now, what's the new difficult version going to be like? Well, oops, let's try that again. Hey, that shouldn't be hard. I got a minus x, I want a minus x. What's the problem? The problem is that I don't have a 1. And these need to be 1 minus something. The something, the guy that's where my finger is, can be as ugly as you like. But this must be a 1. So now I'm going to do, I pull out a common factor of 4. That makes this 1, and that makes this 1/4 x. And then I'm going to think of this as being 1/4 1 over 1 minus quarter x. So that was the original, but this is the way it's going to look. And I can now do the substitution part. What will this x be replaced by? What will this x here be replaced by?
1/4 x.
Okay, now, oh, can I go straight to there and you understand what just happened? Technically, I guess it's 1/4 to the power of n times x to the n. I guess I could write it over here. Yeah, technically it's that, but that's much prettier. Now I'm going to bring this 4 inside, this quarter inside. Won't this quarter join up with that guy? So you're going to have a 4 times a 4 to the power of n. So what does that become?
4n plus 1.
And we are done. Well, we're done for part A, which is find the power series. If they ask you for a radius of convergence, can we just do the ratio test and do the usual stuff? I mean, we've done tons of these, so I'm just going to let that one slide. I'm pretty sure that the answer is 4, but you can double check. Right, are we good with this new problem? Finding a power series where it's not 1 take away something, but 4 take away something, right? So let's see if I can find one. This is like question 2. Oh, don't know why I keep doing that. And I want 6 over 5 minus x. Now, before I even try and do the power series, let's do some surgery on this and get it to look the way it needs to be written as. And it needs to be written as 1 minus something, right? Not 5 take away something, but 1 take away something. So I'm going to take out 5 as a common factor. And we've got that. I'm then going to think of this as 6/5 times that. Are we comfortable with how I got from here to here? Now I know that this little guy here, isn't he going to be the fella that this x gets replaced by? Agreed? That's going to get me this fella. -1 to the n.
Shouldn't it
5
be a +1 or +1/5?
You are right. So let's make that plus so I don't need to change my working. Actually, I kind of like that version because it's got a -1 in it. Oops. So here it's negative. Now it's negative. So that's pretend that was the original question all along. We get to here. We're almost done. I have a -1 to the n. The 6 comes in. I have an x to the n. I want this guy join up with that guy and now have a 5 to the n plus 1. Okay, see if we can find. I think this one's going to need a whole page. So this is going to be like question 3. And now this one doesn't even look much like this. But the first thing I'm going to take care of is 81. Actually, the first thing I'm going to take care of is really just cosmetic. Shouldn't the number be first and the x's be second? It's just the way it's written. It has to be that way, right? Number, letter, right? A little cosmetic, but I needed to do it. I'm going to pull out the 81. And that's going to get me that guy. Right. Pull out an 81, you get a 1 and 181, 1/81th, x to the 4. Take all these pieces and separate them from this piece. Are we good so far? Right, now, this is the guy that's going to use him. Can you see that the guy we're going to use is negative that ugly fraction? So it's going to be x cubed over 81, sigma n equals 0 to infinity of negative 1 over 81 x to the 4, all raised to the power of n. And that is now going to become each of its little pieces. Going to get that guy. X to the 4 raised to the n gets you 4n. And 81 gets you n. Okay, if you bring in x cubed here, won't it just add 3 more to this power? Right, so if you bring in x cubed, 3 more added, 4n add 3. If you bring in an 81 here, you just get an extra power and you get a plus 1 there. So by using algebra techniques, isn't it possible to find power series for lots of fractional functions? Definitely not all of them, but lots of them. Are we good? Nope, done that. Right. So just check I've not got some things I haven't covered. Let's do this one. Right. Now, this one is very similar to question 3, right? So I'm just going to keep question 3 here so you've got a kind of visual clue. And you get 2 minutes. Do the power series for this guy. And there's a kind of helpful template. There's a little help for those who need a kind of push. Okay, let's get started. The 49 plus x squared, I'm going to pull out the 49 and that leaves me with that guy. And then separate it. And don't need this anymore. When you look at this fella, we are going to use that guy there with a negative involved. So it's going to be sigma n equals 0 to infinity negative 149 x squared. I'm going to get a negative 1 to the n. X squared raised to the power of n gets you 2n. And on the bottom, I'm going to get 49 to the n. And then I'll just bring the x inside the sigma and the 49. I hope you got that. And you've now created the power series for this fella. So if I gave you a fraction not unlike this one, do you feel comfortable about the process of converting it to a power series? That's kind of what I hope you've got from today so far. So now I'm going to show you some things you can do to power series. Imagine that you've already found the power series for your function. And I'm writing it down in its very generic way, right? an x to the n, right? You can actually find the power series for this guy's derivative. And all you do is you differentiate it. Now, if you think about this as being an infinite polynomial and you're differentiating it, isn't it just a power rule? So if you multiply this by its power, and then you reduce the power by 1. Now, there's one subtle difference, but it is an important difference. Do you notice that this power series, the original function started with n equals 0, but in the derivative, it starts at n equals 1. And that's not cosmetic, that is important. It has to be there. Why do you think you don't have n equals 0 here? Any thoughts about why n equals 0 would be a bad idea in this power series?
We don't want it to turn completely to 0.
Sure what the answer is. We certainly don't want it to be 0. Suppose I plug 0 in here. What would this power of x be?
-1.
And we know that you don't get negative powers in a power series, right? And so they shouldn't be getting negative powers in its derivative, right? How would you? Second thing is, when you do a derivative, doesn't the constant term get killed? Doesn't the 1 at the beginning or the 4 at the beginning always gets killed off? And isn't n equals 0 the guy at the beginning? So if you start at n equals 1, you've taken care of that, right? So it is kind of important that you do that. Also, if you know the power series for f of x and you wanted to know what the power series of its integral was, here it is. Add 1 to the power, divide by the new power with a plus c because it's an indefinite integral. So if you differentiate this guy, you get the power series of its derivative. If you integrate this guy, you get the power series of its integral. In the integral case, you keep the 0, but you have a plus c. In the derivative case, you lose the 0. Apart from that, it's differentiate or integrate. So let's suppose I tell you I have a power series n equals 0 to infinity, n squared over n plus 1 x to the n, right? I got a power series, and that's what the guy looked like. And I would like to know a power series for its derivative. Well, before I do anything, I remember to start at 1, right? Now, in this particular case, won't you multiply by the power? Reduce the power by 1, but everything else is really just a constant. So everything else is still there. And in some cases, you get things cancelling, and in other cases, things combine. You have now got the derivative of this power series. Try this one. Suppose I have a function and its power series is n equals 0 to infinity of n 5 to the n, or I'll stick a -1 in the n. I'll make this 2n because I want to, and I'll put it over n factorial. That's a pretty ugly looking power series, right? And I would like to know what its derivative looks like. Remember to start at 1. Everything that doesn't have an x, right? All of these terms are constants, right? They're just like the number 42. So they remain totally unchanged. And then don't you just differentiate this guy? Okay. Now in this case, you get what? 2n, x to the 2n take away 1. I just put the brackets around for emphasis. And you should probably tidy up as best you can. Stick a 2 probably here. Combine them to get what? An n squared. That's still there. That's that guy. You still get an n factorial on the bottom. Are you comfortable with the process of differentiating a power series? Make it n equals 1 and then just differentiate the power of x, right? Everything else, keep it, right? Don't change anything yet. If it's x to the n, I guess you'll get n x to the n minus 1. But if it's anything else, don't you multiply by the power and reduce it by 1. Okay. Let's go the other way. Suppose I have a power series. And I would like to know what the power series of its antiderivative is, right? Its integral. Now, when you integrate, you keep the n equals 0. You keep the n factorial. And don't you just integrate, in this case, x to the n. Now, the rule for that is add 1 to the power, right? And then divide by the new power. Oh, plus c. N factorial multiplied by n plus 1 can actually be put together. What do you think n factorial times n plus 1 ends up being?
N plus 1 factorial.
And now you've found its integral. Do one more. suppose I have the power series for the function g of x, and it's this guy. And I'd like to know the power series for its antiderivative, its integral. Keep the 0, and remember the plus c. This guy is fixed. This guy is fixed. This guy is fixed. Just the brackets are for emphasis. Add 1 to the power and divide by the new power. Put everything together, and if it's possible, tidy it up. So I get this guy. And we're finished. So if I give you a power series and I say, find the power series of its derivative or find the power series of its integral, are you comfortable with how the process is going to work? Okay, got some nods. I like nods. So what's left? Well, I've done these questions with the power series already given. You're more likely to get the question one step back. In other words, you have to find the power series first and then differentiate it. So let's see if I can find one in that vein. Okay, this one is like question 9. No, that one's given. Take that back. Come on, find one that's not given. Yeah, this one. Question 5. They want us to find this fella. Okay, I mean the variable's called t, but it could have been called x, y, z, it wouldn't matter. First step. Find the power series for this fella. Okay. Now I'll have to return. Where's my little guy? Okay. We need to look at this fella and see what we've got. Well, I don't have actually that much to do, right? It's basically this guy. So it's going to be t sigma n equals 0 to infinity. And won't this guy here go there? So I'm going to have just t squared to the power of n. Are you happy about this becoming that? Right. The t is here, and the 1 minus t squared basically tells us to substitute in a t squared. And so I'm now looking at n equals 0 to infinity of t to the 2n. And now I have my power series. Now the question is asking us to find the power series of its integral. Right? So I'm basically just going to integrate this fella, right? So it's going to be, do you keep the 0 when you integrate? You do, correct. Not much happening here, so add 1 to the power and divide by the new power, and you are finished. There wasn't really any tidying up to do. You like that one? Here's another one coming up. This is like question 6. And we're being asked to find that integral, or at least the power series. Which means I'm going to, haven't used this one so much, I'm going to use this guy here. So x to the 4, the natural log of 1 plus x is x to the 4 times this fella. So far, so good. Now, not too much in the way of tidying things up. I'm just going to bring this inside and add 4 to the power of x. We got that. Now, if I want to integrate this fella, shall I start at n equals 0 or n equals 1 in this situation?
0.
It's 1.
Still 1. If your guy is 0 and you integrate it, it stays as a 0. If your guy is a 0, it stays as a 0. If your guy is 1, 2, 3, 4, 5, it stays as a 1, 2, 3, 4, 5. If you differentiate it, different rule applies. If you differentiate this, won't you start at 1? If you differentiate this, won't you start at 1? If you differentiate this, you will start at 2. Right? You move up 1. Because in differentiation, you tend to kill off the first guy. So back to this question. It's going to be x to the 4 times this fella. And I should say the integral of this fella, because I've already done all the hard work, right? So this is the guy I'm going to integrate. Add 1 to the power and divide by the new power. And everything else stays put, and you got a plus c. So actually the integration of the power series really revolves around using the power rule on whatever the power of x here is. Oh, and remembering your plus c. Are we good? A little hiccup there, but are we good? Okay. Our last question. Pick a version of this fella. Okay, in this case, you don't have to worry about finding the power series because it's given to you. What you're being asked to do here is find the power series for its first derivative. Now, this guy starts at 1. If you differentiate, what will the new one start at?
2.
2. Multiply by the power, reduce the power by 1. And if it is necessary, tidy it up. Fixed it. There we go. So won't the n cancel one of these? And now we have x to the n minus 1 over n squared. Of course, there's no reason in the world why we can stop at the first derivative. Couldn't we differentiate the first derivative and get the second derivative? only now we start at what value of n?
Three.
Right. Every time you differentiate, you have to move up one. Now, multiplying by the power and reducing the power by 1. In this case, would you agree there is nothing to simplify? That's as good as that's going to get. Now, in all of these particular kinds of questions, you're being asked to find either the radius of convergence or the interval of convergence, in many of them at least. So that's the bit that I've kind of skipped. So I think let's do it for that one, right? So for the second derivative, which is this particular power series, let's find the radius and interval of convergence. Right, so it's going to be the limit as n tends to infinity of an plus 1 over an, which is right, n plus 1. You got to be a bit careful here. What would n minus 1 be if you made the n an n plus 1? What would that become?
N.
Yeah. If you made this n plus 1, and then you take away 2 from it, do you see how that becomes n minus 1? And if you make this guy n plus 1, I think it's a little bit more obvious, you get that. And then you turn everybody upside down. There's not an awful lot you can do except n cubed, and then an n minus 1 and n plus 1 squared. What happens when you take this power of x and you cancel it out with that power of x?
The bottom one is left with the power of -1.
Which is the same as the top one being left with the power of x. One over x to the minus 1's a bit clunky, isn't it? Better to call it x. Isn't the top guy going to win by 1? Now, this ugly looking thing here, I know what the answer to that is. Hopefully you can tell me it as well, just by looking. What's the limit of n cubed over n minus 1 times n plus 1 squared as n goes infinite?
1.
Is 1. Now, you want to prove it? Well, if we had time, I would. Wouldn't you FOIL that whole thing out? Wouldn't you then divide top and bottom by n cubed and then do the brute force? Or do L'Hopital lots of times if you wanted to. So we now know that. Of course, doesn't that mean that it's only going to converge when the answer to the limit is less than 1? So we have just found our radius of convergence. It is 1. And now we're going to do the possible interval of convergence. Right. Well, that means I have to test 2 situations. -1 and then +1. Okay, if you go here and you make x -1, let's see what it turns into. Right, sorry, -1 all over n squared. Okay. I'll just write that again because it's so ugly looking. Now I'm going to have to cut some corners here. Would you agree that's an alternating series? Right. Can you trust me that its limit would be 0 as n goes infinite? Can you also trust me that it's decreasing, which means that this converges? Which means you can use -1, so it's now a square bracket. Right, try the second one now. When you make x equals 1, well, you might be saying, what about the n equals 3? The n equals 3 does have no significant effect on whether a series converges, right? N equals 0, 1, 2, 3. If they converge, they all converge. If it diverges, they all diverge. So I really don't pay too much attention to the start value. It has no significant effect. Now, if you plug in 1 here, you will basically just get that guy times 1 to the power of n minus 2, but it's still 1, right? That one's a bit trickier. And if I had time, I would do the full proof. Do you know if that guy is going to converge or diverge just by looking at it? Because I do. Maybe you can join me.
Diverge.
Right. Are you comparing it to a 1 over n? And that means limit comparison test. Can you pretend I did the limit comparison test and it worked? It diverges. Because isn't 1 over n I divergent is a harmonic guy. So our final answer is that fellow there, -1 to 1. And its radius of convergence is 1. Okay, everybody say hi. And when we come back tomorrow, we'll be on our next section. I think it's called something like applications of power series. I think that's its title. So that's a cool thing to look forward to. Bye-bye. I'll hang about if you have any questions, homework or otherwise.
Thank you.
You're welcome. Okay, who wants to start then? Who's got the first question? Emma, ladies before gentlemen, what you got?
Okay, so I was doing math homework yesterday and I looked up how they did number 3 because I had no idea.
Number 3 from what section?
11.9.
Okay, so I'll look that guy up, and I don't know how they did it, but I'll show you how I would do it.
Well, you did one like it in class today.
Right.
But
Yeah.
it looked really different because they did some interesting things, and I wish I could just take a picture of my work for you. So when they got it,
Well, I can do something here if you want to. I'm going to let you share your screen. So here we go.
well, that's not going to do me any good.
How come? It's in paper?
Yeah.
Okay, it won't do any good at all then. If it makes sense to you the way they did it, then by all means keep doing it that way. If the way I did a similar example today made more sense, I would suggest you do it that way. It's just, what's that phrase? There's more than one way to skin a cat.
Yes.
So there can be more than one way to do a series question.
So you can get 2 really different looking answers and they both mean the same?
Well, you can do something 2 totally different ways, but the final answer will be the same.
Okay.
Right. Is that enough, or do you want me to actually do my version of 3 if you've got the question in front of you, and I'll show you what my answer is?
Yeah.
Okay. So what was the power? What was the function you're trying to get the power series for?
X squared divided by x4 plus 16. It's
Okay.
the same one you just did today.
Right. So they already have an answer. N equals 0, infinity, and you plug it in, right? So as long as I get the same answer as them, hopefully that'll convince you that my way works as well, right?
Sure.
Okay. So I would think of this as x squared, and I would think of it as that guy. I'm trying to find my little formula sheet that I've been using today so we can just look at, here we go. This fella has got 16. That's bad news. So what I'm going to do is I'm going to pull out that 16 and do 1 plus a 16th to the x to the 4, right? So what we now have is this guy times this guy, right?
Yes.
So far, so good. Now, this fella is him. So what that tells me is that I can do sigma n equals 0 to infinity. And this guy should be him, so that makes it a negative 1/16 x to the 4. So I'm going to have this fella, negative 1 to the n on the bottom, 16 to the n, and x to the power of 4 raised to the n gets you 4n. And now I'm going to bring the other guys inside. This 16 joins up with this 16, and that gets you that guy, this fella, and x squared joined onto that just adds another 2 to its power. And there's my answer. Right, do they have the same answer, or do they have an answer where there's a 2 to the power of some big ugly guy in the bottom?
Yeah.
Okay, let's show you what that's all about. I don't think you need it, but if they want it, you've got it. You have to recognize that 16 is actually 2 to the power of 4.
Yes.
So if somebody says 16 to the n plus 1, you can think of it as 2 to the power of 4 to the n plus 1.
And then you would get, okay.
So that's where that came from. That's really just style points. And I guess the question you have to ask yourself is 16 to the power of n plus 1 better looking or uglier looking than 2 to the power of 4n plus 4? That's a bit like a beauty contest. You know, some people like A and some people like B. You know, I don't think either of them is worse or better. I think it's just taste. Now, I would hope that WebAssign accepts the 16, because if they do, then we have no problems. If WebAssign does not accept that, then you will have to figure out how to turn it into that. Some of the questions I've seen that's possible for is some like that, because that would be 5 squared to the n, so you could end up with 5 to the 2n. On the other hand, 13 to the power of n is as good as it's ever going to get, right? You can't really do anything to that one. And other combinations, 6 to the power of n, I don't think you can do anything really useful with that one either. So you're probably only going to be looking at, you know, squares, you know, 25 and 49, or numbers like 8, 16, 32. They may be changed. But I think the vast majority of them are probably just going to be what you got the first time.
Okay, that's what I needed. Thank you.
Okay, you are good. Who's next on my list? Feel free to hang about if you want to. Right, what you got? Sam, you got a question, or are you just listening because you want to?
Very quick question, and then just listening in. So with the last question that we did today,
Oh, yeah, I'll try and find it. What about it while I'm looking?
you said that we would use the limit comparison test. I was also wondering if we could just use the comparison test.
I would have to look at the specifics. I tend to avoid the comparison test and only use it when there's an ugly guy in the top, like a sine or an e to the 1 over n. It is sometimes possible that you can use it. For some reason, I can't seem to find the guy at all. And I've thrown it away because I haven't moved anything.
I can tell you what it is.
Oh, I think I have it. No, I don't. Yeah, tell me what it is.
So
Let me try to find it.
oh wait, pick up that black piece of paper with the black writing.
This guy.
Yes, that one.
And it became this guy. Here we go. We found him.
Yes.
So n minus 1 over n squared. If I wanted to use just a comparison test, I would have to prove that this guy is bigger than I diverge. I believe that that's not true. Pick a number, 7, right? If I picked 7, is that guy bigger than that? Well, is 649s bigger than 17? The answer is no, it's not. So the limit, so the comparison test would not work. But in a different world, this would be true. This is bigger than that. I'll try and prove it to you. Isn't 1 over n squared plus something bigger than just 1 over n? So the comparison test it's just best to avoid it and always go limit comparison test. Now, you're going to do a limit comparison test with that guy. The math is not that horrendous. It does come out pretty easily. And I believe the limit you get is 1, which is fine. Because in the limit comparison test, you just need a number that's not 0 or infinite. And it behaves the same as the one you're comparing it to. And that's just a safer bet. Keep the limit comparison test, keep the comparison test to ugly guy on top situations, like that. And